The next best thing to knowing something is knowing where to find it. A quote by Samuel Johnson. Greetings to all. In this PowerPoint presentation, I and my fellow colleagues will be going over the experiment overview pertaining to the pressure drop in pipes, the materials and methodology section, a discussion of the results obtained, as well as a closing word of the experiment. Pressure drop, otherwise known as head loss, is simply the difference in total pressure between 2 points in a fluid carrying network of pipes. In industry, engineers need to know and understand how to calculate head loss so as to design appropriate systems such as the one displayed on this slide. Important parameters that influence head loss include pipe diameter, the flow rates of the fluid, surface roughness of the pipe network, and the types of fittings. Furthermore, the altitude, position, and the length of the pipes also affect pressure drop. With this understanding and application in industry, product quality can be manipulated and economic feasibility can be maximized. The main objective of this experiment was to observe and explore fluid behavior through measuring head loss under the previously mentioned parametric conditions. By doing so, a clearer idea of how particles behave in the molecular regime is established. Pressure drop in horizontal pipes has been studied by a number of researchers to develop empirical models applied in industry. Fundamental equations and models such as the orifice formula, the Hagen-Poiseuille equation, the Reynolds number, and relative roughness have been employed in the analysis of this experiment.
This section focuses on the materials and methodology employed in this practical. The benchtop setup of the fluid flow system used in this experiment is shown in Figure 1 on the slide. The system was initially calibrated. For this part, water was allowed to pass through a single pipeline and collected into a tank. This was done in triplicates for 5 different rotameter heights. For each run, the volume of the water collected and the time of collection were measured using a measuring cylinder and a stopwatch respectively. The data obtained was then used to calculate the volumetric flow rate, which was further used to construct a calibration curve of volumetric flow rate against rotameter height. The second part of the experiment involved investigating the effects of parameters affecting pressure drop across a pipe. Again, water was allowed to flow through the pipe of interest at different flow rates by varying the rotameter height, and pressure drop was determined by measuring the inlet and outlet pressure. This was repeated by passing water through pipelines of different sizes, material types, and fittings, and the specifications of each pipeline are shown in Table 1. The data obtained allowed us to analyze the effects of flow rate, pipe diameter, material type, and fittings on pressure drop across the pipe.
Now we turn to section 3, which is the results section. In this section, we try to see how our results and our findings measure up with the already existing theory. In the first slide, a graph of rotameter height versus volumetric flow rate is drawn. A line of best fit with a positive gradient indicates to us that there exists a directly proportional relationship between the volumetric flow rate and height of the rotameter. This is perfectly in conjunction with the orifice formula. in that when the float moves up in height, the area also increases in value, therefore causing the volumetric flow rate to also increase. Now in this slide, we'll look at the relationship between the volumetric flow rate and the pressure drop. We come to realize that another linear relationship with a positive gradient exists. This is reminiscent of the Hagen-Poiseuille equation, whereby a higher flow rate results in rapidly moving molecules crossing over a point in time, and this elevated interaction of the molecules leads to a higher pressure loss. Now in the next two slides, we're investigating the diameter of the pipe. We're going to look at two different material types, that is the steel pipe and the plastic pipe. For each, we'll look at the different diameters and how they affect the pressure drop. We come to realize that the larger diameter leads to a lower pressure drop in both pipe materials, and this happens because the fluid is able to move more freely and encounter less friction against the walls of the pipe. There also exists a relationship between the relative roughness and the diameter of the pipe, and it's given below. Now we turn to looking at the material type. We're going to compare steel and plastic and steel and glass respectively. In comparing the steel and the plastic, there was a bit of a discrepancy in that it seemed that the plastic material showed a higher roughness than the steel material, which is inaccurate because it is common in literature that the steel has a higher roughness than the plastic. This may be due to an error in calibration or the measurements. The comparison of the glass and the steel on the other hand gave the anticipated results in that the pressure drop across the stainless steel pipe is higher than that of the glass pipe. Lastly, we looked at pipe fittings. We chose to make this analysis between pipe 5 and pipe 6 because they are the only two with elbows, while all the other pipes are straight. Pipe 5, which is an angle of 45 degrees, seemed to show a higher pressure drop. This is because bends increase collisions amongst the particles, therefore a smaller angle will result in more collisions and thus a higher pressure drop. And that concludes the results section.
Thank you. Now for the conclusion and recommendations section. After consolidating and summarizing what has already been mentioned and discussed by Moses under the results and discussion section, we have reached the following conclusions. Firstly, that pressure drop increases with increasing pipe roughness. That is to say, the rougher the pipe, the higher the pressure drop across that pipe. Secondly, pressure drop increases with increasing degree of bend. So the more bend a pipe is, the higher the pressure drop across that pipe. We have also come to the conclusion that the Hagen-Poiseuille equation was accurate in predicting the trends and relationship of the parameters that were being changed in this experiment. From the equation, we were expecting a linear relationship between pressure drop and volumetric flow rate, and we were also expecting an inverse relationship between pressure drop and pipe diameter, and both those expectations were met. The following are recommendations that we believe would help in improving this experiment. Firstly, the working environment must be clean. This helps avoid unnecessary inaccuracies that could arise from untidiness and/or uncleanliness. Secondly, the valves should be allowed to run for longer. This ensures that any bubbles that might be in the system are eradicated. And also, there must be a proper ventilation system where this experiment is being conducted. This helps to achieve a constant ambient temperature so that there aren't any pressure losses due to a change in temperature. Thank you.